All right, let's jump right in. We usually think that to make progress, you have to aim for perfection, right? You fight to crush every single tiny error. But what if in the really strange world of quantum physics, the secret to a huge breakthrough isn't about winning that fight at all, but about finding a really, really clever compromise? Today, we're going to look at an amazing new strategy in quantum sensing that does exactly that. So first off, why is everyone so excited about quantum sensors? Well, the potential here is it's just revolutionary. We're talking about technology that could give us GPS systems so ridiculously precise they can navigate you indoors, or medical gear that can pick up the faintest signals from your brain, or even new ways to find resources buried deep in the earth and clocks so accurate they literally change how we measure time itself. And that really is the big question, isn't it? If these sensors are so powerful, why aren't they everywhere? Well, the answer is kind of ironic. The very thing that gives them all this incredible power is also their biggest weakness. To get a handle on that, you've got to look at the basic building blocks of these sensors. They're called qubits. Now, qubits are the fundamental pieces of quantum information, and when you link them together in this very special way, you create something, well, something extraordinary. It's like a super sensor. That special link is called entanglement. And you can think of it like this. If a single qubit is a talented solo musician, then a group of entangled qubits is like a world-class orchestra. They are all playing in perfect, instantaneous harmony. They're so connected, they basically act as one single super-sensitive system, amplifying any little signal they pick up. And this is where it gets just wild. Check out the huge jump in performance here. Let's say you've got 100 qubits. If they're just working by themselves, unentangled, you get a sensor that's maybe 10 times more sensitive, which is, that's pretty good. But if you entangle those exact same 100 qubits, whoa, your sensor is now 100 times more sensitive. That's not just better, that's an absolutely massive leap in power. Okay, but with great power comes great vulnerability. There's a villain in our quantum story. This constant, unavoidable enemy that threatens to ruin everything. And that enemy is noise. Now, in the quantum realm, noise isn't just a sound. It's any tiny little disturbance from the outside world. We're talking a tiny shift in temperature, a microscopic vibration, even a stray magnetic field from your phone. For us, we wouldn't even notice this stuff. But for a super delicate quantum system, it's like a hurricane that just comes in and wrecks its fragile state, completely wiping out the information it's holding. And this slide right here just lays out the core problem perfectly. The very entanglement that makes the sensor so powerful also makes it incredibly fragile. It's a classic catch-22. The more powerful you make it, the easier it is for noise to just come in and knock the whole thing over. So for years, scientists tried to fight noise head-on, build a perfect shield, but that turned out to be almost impossible. So they came up with a twist. A new strategy that seems to go against everything you'd think would work. I mean, the old way of thinking made sense on the surface. You build your sensor, you see that noise has caused some errors, and then use these really complex quantum error correction techniques to try and fix every single error. The goal was total, absolute perfection. But then you get this breakthrough, and it's all summed up in this one quote from NIST physicist C.J. Lin. He says, "We only need to correct it approximately rather than exactly." Think about that. It's a total shift in thinking. Instead of chasing this impossible goal of perfection, what if you just aim for good enough? So this is the key insight. The new strategy is to intentionally let some errors slide. They designed the system to only fix some of the errors from noise, and what they found was amazing. It turns out the very act of trying to fix everything perfectly was actually making the system weaker and more fragile. By letting go of perfection, they actually made the sensor stronger. And this all leads us to the big payoff, the winning trade-off. It's just a beautiful example of how, in the real world, the best solution on paper isn't always the one that actually works. Let's break down what that trade-off looks like. Okay, this table lays it all out nice and clean. Look at the first row. Unentangled qubits are okay, and they're pretty tough against noise. Then there's the old way, entangled with perfect correction. Yeah, it has the highest sensitivity in theory, but its robustness is so low that any real-world noise just wipes it out. But now, look at that last row, the new approach, with approximate correction. You get high sensitivity and high robustness. You give up a tiny bit of theoretical power, but you gain a system that can actually survive out in the real world. That's the sweet spot. So what's the bottom line here? It means we've learned to accept a small, calculated hit to performance in exchange for a huge, massive gain in toughness. The sensor you end up with is still way more powerful than one with unentangled qubits, but now it's actually durable enough to work outside of a perfect lab. This isn't just some cool idea. It's a real, practical roadmap for building the quantum sensors of the future. This whole idea of meeting noise halfway instead of trying to beat it, it just blows the doors wide open for actually building all that amazing technology we talked about at the start. So it leaves us with this really exciting question. Now that we have a real path forward, what secrets about the universe, about our own bodies, and about our planet will these incredibly powerful and now newly robust sensors finally let us discover?